welcome back. In the previous lecture we talked about Cauchy's integral formula. So today we will consider one of its generalizations. So we will talk about derivatives of analytic functions. And let's discuss the formulation of the theorem that generalizes Cauchy's integral formula. So suppose that we have a function f, and function f is analytic everywhere inside and on a simple closed contour traced in a positive direction. And if z is any point of interior to contour C, then its derivatives of all orders are also analytic functions at point z, and the following formula holds. Right? Let's let's discuss the formula. So what do we have here? We have fn in the parentheses. I put the order of derivatives. So if n equals 0, we will have derivative of n 0th order. That would be our function itself. And here we have n factorial. Factorial means the product, right? 1 times 2 times 3 up to n. And you probably remember that 0 factorial equals to 1. This is convention. 1 factorial equals to 1 and 0 factorial equals to 1. So then when n equals 0, here we'll have 1 over 2 pi I integral along C and our function, and here s minus z, n will be 0, so we will have just regular Cauchy's integral formula, and we can use this formula to compute derivatives of our analytic function. And if we just move this factor to the other side, which is convenient for computations, then we can have our formula written in a form convenient for computations, and integral of such a type equals 2 pi I over n factorial and derivative of our function evaluated at point z. So let's discuss the proof, but first let's just write a couple of specific formulas. So as I mentioned, when n equals 0, let's write this. When n equals 0, n equals 0, then we will have just that f of z equals integral along C. So what is our C? C is a contour, right? Simple, closed, positively oriented, and point Z is somewhere inside. So in the last lecture we called this Z sub 0, but it doesn't really matter, right, what name we will give to it. And in our integral, point S is point on the contour C. So then we will have f of s ds s minus z. Right, when n equals 0, we will have, and I always forget the factor, it will be 1 over 2 pi I. So this is the formula we discussed. So now let's see what first derivatives looks like. Let's write the case when n equals 1. When n equals 1, our formula will give us that f prime at z equals 1 factorial is 1. Here we will have 2 pi I, and then we will have integral along contour C, f of s ds, and here we will have s minus z, and now n equals to 1, so we will have it squared. right? So just when n equals 2, then we will have f primes at z equals, then we will have now 2 factorial. 2 factorial is 1 times 2. 1 times 2 is 2, divided by 2. 2 and 2 will be cancelled, so we will have just 1 over pi I. And integral along contour C, f of s ds, and here we will have s minus z to the now n equals 2 cubed. Okay, so here are the formulas. So let's see from those formulas how we can, not very rigorously, but if we formally, let's look at this formula, right? And formally differentiate this with respect to z. So z we have only in the integrand, so let's take a look at the integral and differentiate it with respect to z. Then f of s doesn't depend on z, it can be pulled out. So what you're differentiating, actually, you are differentiating 1 over s minus z, you differentiate with respect to z. And you use the chain rule, so you have s minus z to the negative 1, it will be negative 1 over s minus z squared. And then you need to differentiate inside, and differentiating inside will give you, with respect to z, will give you negative 1 times negative 1. So this negative 1, first negative 1, and the second negative 1, this and this will be cancelled out. So finally we will have just 1 over s minus z squared. That's what we have in this formula, right? So this is the idea. And now let's just, so how we can do it more rigorously if we use the definition of derivative. So let's apply the definition of derivative to this function f of z, and let's obtain this formula. This I don't need. I will start from here. So what is the definition of derivative? It's a limit, right? If we take f of z plus delta z minus f at z divided by delta z when delta z approaches 0. And that will give us the limit delta z to 0, and then it would be 1 over delta z, and I will put parentheses here. So what is f at z plus delta z? So this is my formula for f of z. So it will be 1 over 2 pi I integral along c f at s ds over s minus z minus delta z, right? I need to plug, instead of z, I need to plug z plus delta z. And then will be minus the second integral, minus 1 over 2 pi I c f at s ds s minus z. And then let's rewrite these two integrals as one integral. So what we will get? We will get is, it would be equal to the limit delta z goes to 0, 1 over 2 pi I integral along c. Delta z does not depend on s, so I can move it inside, outside freely. I will move it inside now. So what do I have? I have here, it will be, I will put it this way. So it's 1 over s minus z minus delta z minus 1 over s minus z. And here I will have f of s ds over delta z, right? So f of s I pulled out, and what I'm going to do, I'm going to find a common denominator. So this is one expression, this is another expression. Common denominator, and see how things would be simplified. I don't think I need this, so I will remove this. And then we will have limit delta z approaches 0, 1 over 2 pi I, integral along c, and the common denominator would be s minus z minus delta z times s minus z. And here we will have the first fraction has to be multiplied by s minus z, so we put s minus z, and the second fraction must be multiplied by this expression, and we need to change signs everywhere. So I will put minus so far, minus, and then s minus z minus delta z. And then the whole thing would be multiplied by times by f of s ds over delta z. That's what we have there. And then let's see how we can simplify. So we can simplify things. We can see that this s and this s will be cancelled, and then this negative delta z will become positive delta z here. They also will be cancelled, and we will end up with minus and minus positive delta z, right? So I will write its limit. Delta z goes to 0, 1 over 2 pi I, integral. So here we will have delta z times f of s ds, and divided by s minus z minus delta z times, I need to erase this, sorry, so times s minus z, and we also have delta z here in the bottom. So delta z and delta z will be cancelled. So finally we have limit delta z approaches 0, 1 over 2 pi I, integral. And we have f of s ds, and in the bottom we have a product of s minus z minus delta z times s minus z. And now let's compute the limit. What what happens if delta z approaches 0. If delta z here approaches 0, then this whole expression approaches just s minus z. And then we will have s minus z times s minus z, so that will give us 1 over 2 pi I integral along c f of s ds s minus z squared. So, and that's what we wanted to get, right? So for n equals 1 for the derivatives, we just wanted to have the formula 1 over 2 pi I, and here wanted to have square. That finishes the proof, and of course you can continue these to compute second derivative and so on. So now let's consider examples. Let's consider our first example. So examples would be related to this formula. So here is our first example. Evaluate this integral. Integral is taking along a circle of radius 1, and let's assume that, suppose that it's given that the contour is traced in a positive direction. And here we have this function. So we can see that exponential function is an analytic function, and in the bottom we have z to the fourth. And if we compare our integral with what we have here, right, it tells us that our z sub 0, our special point, is 0, right? So, and here the power is n plus 1. So I can rewrite, I cannot say intentionally, but it's good to use different notations so you don't think about notation. So we can write here e to the 2. If you want, I can rewrite here, for example, if it's more convenient, in the notations that's in this example s, and here it will be 2s ds, and here it will be s minus 0 to the fourth, so 3 plus 1, right? So this is how these two formulas are related. So, and then we can see that then the value of the integral would be equal to, before that, let's see if our special point, which is 0, is inside the contour. Our contour is a circle centered at 0, radius 1, so our point 0 is inside, right? Because what is important, whether or not our point is inside. The point is inside, so we will have that the value of our integral would be equal to pi I, and then n equals 3. So here we will have 3 factorial, and then we need to take our function. Our function is e to the 2s. We have to differentiate it 3 times with respect to s, and then we have to plug s equal 0. Right? So then what we will have is, let's notice when we differentiate, I will go back to my original notations just not to mess up. So this is kind of, here I showed how these two formulas are related. So in my original notations, I will rewrite this as 2 pi I over 3 factorial e to the 2z, third derivative with respect to z when z equals to 0. And so let's differentiate our function e to the 2z once. what happens if we differentiate our function e to the 2z once with respect to z. We will have still e to the 2z, and then using chain rule it will be multiplied by 2. When we compute second derivative of e to the 2z, then it will be first derivative of this, and we will get 4 e to the 2z, and the third derivative will give us 8 e to the 2z. And then what we need to do, we need to take this function and plug 0. So we will have is 2 pi I over 3 factorial, then 8 e to the 2 times 0, 0. E to the 0 would be 1. So now let's simplify. So what we have here? We have here 2, we have pi I. What is 3 factorial? It's 2 times 3. And here we will have just 8. And then these 2 and 2 can be cancelled. So the answer would be 8 pi I over 3. So our computations are done for this example. Let's consider the second example. So our second example is again evaluate integral. So we have 1 over z squared times z squared plus 4 dz, and we have 3 different contours. So we assume that each of them is traced in a positive direction, and all of them are circles. So let's discuss the case A. So in the case A, we have z plus 1 equals 2. That would be a circle. Center of this circle is at the point -1. So we put here -1 and radius 2. So this would be our circle. This point would be 1. This point would be -3. This is traced in a positive direction. It's like this. So now we have the circle. So our next step, what we need to figure out is how many out of these singularities are inside. So we have point z equals 0, first of them. So this point z equals 0 is located here and obviously is inside. Then we have 2 more points. We will have, when we talk about z squared plus 4 equals 0, it means that z equals plus or minus 2 i's. So we need to find out whether or not our points plus 2i and -2i are inside this circle. So let's see what would be the equation of this circle. We have here x plus iy, so modulus would be x plus 1 squared plus y squared, and square root equals 2, so this is equals 4. Right, so this is the equation of our circle. And now to find out the intersections with the y-axis, we will put x equal to 0, right? And if we put x equal to 0, we will have here, it will be 1, so y squared equals 3, and y equals plus or minus square root of 3. So here are the points. This point is square root of 3 times I. This is point is negative square root of 3 times I. Square root of 3 is approximately 1.7, so it's less than 2. It tells us that our points 2i and negative 2i, they are somewhere outside. They are somewhere here and there. So we don't have to take them into account because they are not inside of our circle. And so now what do we have if we look at our integral? So what is our function f? Right, we will be applying this formula, so our function f in this case would be 1 over, I will rewrite this integral in the form. So our contour is given, it's z plus 1 equals 2. Our function f, I will write here on top, it will be 1 over z squared plus 4 dz, and here I will just have z squared. So I will rewrite the formula in this way, and we know that our singular point is 0, so according to this formula we need to write that would be 2 pi I, right? So what is our n? So here we have n plus 1, we have 2, so it means that n equals 1. Here we will write over 1 factorial, and then we need to differentiate our function exactly one time, so it will be 1 over z squared plus 4 derivative, first derivative with respect to z, and then in the end we need to put z equals to 0. So now let's differentiate our function. What we will have, it will be 2 pi I over 1, right? 1 factorial is 1. What is derivative of this? A derivative, we have z squared plus 4 to the negative 2, to the negative 1. So derivative, when we use the chain rule, it would be negative 1 over z squared plus 4 squared times derivative of inside, which would be 2z. And then we need to plug z equals to 0, which tells us that we did a lot of work, but the answer would be just 0. So this was our first contour. So now let's discuss the case B. In the case B, we repeat exactly the same steps, right? So our contour is now z minus 1 equals to 2, and that would be contour. That would be a circle centered at point 1. So this is our center, point 1. Radius is 2, so that would be point 1, 2, 3. That would be point negative 1. So this is our circle, right? This is its center, and it's again, then we look at our integrand. So we have point 0. Point 0 would be still inside, and these 2 points, 2i and negative 2i, right? We can look at this circle. Of course, we can repeat the same computations just by putting here x minus 1, but it's obviously that we have just a reflection. This is a symmetric situation, so these 2 points again would be square root of 3i's and negative square root of 3i's, and our points 2I would be somewhere here, 2I and negative 2I, they will be outside. And the points would be outside, so the value of the integral along this contour z minus 1 equals 2 of the function 1 over z squared plus 4 dz would be again 0, because we have exactly the same singularities inside. So now let's look at the case, at the third case. So what we will have in this situation. In the third case, we have integral, case C. We have the same integral, contour is modulus of z equals 3 traced in a positive direction, and we have 1 over z squared plus 4 dz. Let's make a picture. So this picture is the first important step because it helps us. Now we have a circle with radius 3 centered at the origin. That would be our circle. So this is its center. This is 3, negative 3, and here we'll have 3 i's, negative 3 i's. Now let's mark all of our singular points. Our singular points would be, again, at 0, right, from this term. And from this term, we will have 2i and negative 2i. So actually, we can, maybe it would be helpful if I rewrite the integrand just by factoring the denominator. So if I will rewrite this as integral z equals 3, 1 over, and here we'll have z squared, z minus 2i, z plus 2i, dz. And now let's look at our contour. Contour is traced in the positive direction, so contour clockwise. And then we can start deforming our contour. So instead of our contour, if we take this contour, right, homotopic to each other, so if we can make continuous deformation. So in other words, if we deform contour in such a way that all of the singularities are still inside, and then we can deform our contour into something like that. So it's still traced in the same direction. And then see what happens here. So here, if we really make these two lines close, so then we will be integrating from here to here in one direction and then backwards along the same line if we make them really, really close. So these integrals will not matter. And finally, we will get from, let me rewrite this a little bit bigger. So what do we have? What do we have here is something like this. positive direction. And then we can just remove these two parts, right? Because we can say this would be integral along this contour. First, let's call it C1. And then we have this, say, C2 and C3. These two integrals along the same line will be cancel each other. And then we will have, say, it will be C4. Then here we'll have C5, C6. They will be cancel each other. And then we will have integral along C7. So finally, we can switch to what would be important in these our singularities. So we will have this contour, we will have this contour, and we will have this contour. Right? So our new three contours, let's call them, say, gamma 1, gamma 2, and gamma 3. And our integral can be rewritten as three integrals of the same function. Function we will keep the same along gamma 1 plus integral along gamma 2 plus integral along gamma 3. Right? Each of them has exactly the same integral. But what we can gain from here, from this? So we can gain the following. Then we kind of split our whole integral into some sub-integrals when each integral has each contour has only one singularity inside. So now the situation with contour gamma 1 can be computed in following way. So let's see, if we have integral along gamma 1, here is our function 1 over z squared, z minus 2i, z plus 2i, z plus 2i, and then dz. How we can rewrite our function in this form? So what is inside? Inside we have only the singularity 2i's. So singularity 2i's, so I will have here z minus 2i's, and my function f in this case would be 1 over z squared, z plus 2i's. This is my function dz. And so this function in the top is analytic function inside the contour. And the only singularities that we have inside the contour is z equals 2i. So then I can use regular Cauchy integral formula. In my case, n would be 0. So then we will have 2 pi I, our function 1 over z squared, z plus 2i's. We don't have to take derivatives because now n is 0, so 0's derivative, it's function itself, and we have to evaluate this expression at the point z equals 2i. So let's plug 2i here. When we will plug 2i squared will give us -4, and then here we will have 2i and 2i, it will be 4i's. So we have 2 pi I, and in the bottom we have -4 times 2i's. So I and I can be cancelled, and 2 and 2 can be cancelled. So what we have, oh sorry, not 2i, 4i's. 4i's, 2i's and 4i's. So I and I will be cancelled, and we will have pi over 8. So this whole thing would be equal to negative pi over 8. So this would be our answer for only this first integral. Then let's compute the integral along this gamma 3. We know that integral along gamma 2 we already computed, because integral along gamma 2 would be the same as the first two integrals, where we had just one point, 0, one singular point inside, which was 0, so we know that integral would be 0. This one, we know that the value of this integral, this value will give us 0. We computed value of this integral. Value of this integral equals to negative pi over 8. And now let's compute the last integral, which you probably can guess how to compute. It will be just exactly the same as integral along gamma 1. So integrals along gamma 3 of our function 1 over z squared, z minus 2i's, z plus 2i's, dz. And now we will act similarly. So the only point that is inside is negative 2i. So now we will have gamma 3. We will put into denominator z plus 2i's, and our function f would be 1 over z squared, z minus 2i's, dz. This is our function f, and again, like in this case, we just need to use the simplest version of Cauchy integrals formula when n equals 0, so we don't have to compute derivatives. We just need to evaluate our function, so it will be 2 pi I, and then our function 1 over z squared, z minus 2i, evaluated at the point z equals negative 2i's, which will give us 2 pi I in the bottom, negative 2i squared, negative squared is a plus, and then we will have just negative 4, and here we will have negative 2i and negative 2i and negative 4i's, so the value would be just I and I is cancelled, minuses are cancelled, so we will just have pi over 8 with a plus. So now we have pi over 8 with a plus, and finally, what is the total answer to this example? We have to add negative pi over 8, we have to add 0, and then this integral would be just pi over 8. When we add them all together, we will have 0. So the answer is 0.